For this video, we're going to be looking at the motion of an object in an electric field. So in this situation, we've got a charged metal sphere. We're going to call it A. It's going to have a positive charge on it. And then we're going to have a second sphere, which is kind of like an air hockey puck with a sphere. It's able to move on this flat surface, and it's actually going to be a frictionless surface. So the idea is this one is stationary, this one is able to move. Because this is positively charged and this one's positively charged, there will be a repulsive force, and B should be moving towards the right. It starts off being a separation distance of 25 centimeters. So we're going to figure out how quickly this thing is moving as it's gone further away. The charged sphere A is fixed, charged sphere B is free to move, and we're going to have it moving without friction. So the charge on the A sphere is 57.6 microcoulombs. The charge on sphere B is 39.2 microcoulombs. So if we put this into coulombs, 57.6 times 10 to the negative 6 is your micro. So now we put these in the proper units. So we want to figure out the speed of that sphere B when it is moved to a position of 98.5 centimeters away. So here is the original position of it, and we want to figure out when it's been pushed to a position of 98.5 centimeters away, how quickly will it be moving. So if we look at Coulomb's force, the equation is K, Coulomb's constant, times the product of the two charges divided by the distance of separation. So we could very easily plug in the variables for this question and figure out what is the electrostatic force of repulsion when B is right here. So there is a problem with this type of solution. As object B is pushed towards the right, the separation distance gets larger. As the separation distance gets larger, the electrostatic force or Coulomb force will actually decrease slightly, which means the acceleration decreases. So the issue is that because we have the electrostatic force continuously decreasing as B moves away, we're not able to use Newton or using kinematics without calculus. So there's no way for us to solve it just using F equals ma. So what we're going to do is solve for the speed using a change in electric potential energy. So the electric potential energy of the field, EE, is equal to K Q1 Q2 over R. So this will give us the electric potential energy of the field. So we originally had the sphere B sitting at this position, which is 25 centimeters. Then at some point later, it'll be moved down to 98.5. So I'm going to mark position 1 at the 25 centimeter distance, and we want to figure out the energies at that point. So total energy of the system is going to be a combination of electric potential energy and kinetic energy. Because the object is initially at rest, we can say that our kinetic energy is 0. So the total energy of the system is just going to be the electric potential energy of those two spheres. And we're going to be using the equation KQ1 Q2 over R. We plug in our variables. So Coulomb's constant, 8.988 times 10 to the 9th. The units are newtons, meters squared per coulomb squared. QA was 57.6 microcoulombs, or 57.6 times 10 to the negative 6 coulombs. Charge on B was 39.2 microcoulombs, or 39.2 times 10 to the negative 6 coulombs. The distance of separation was 25 centimeters, or 0.250 meters. So we multiply the top. And when we multiply the top, we get 20.294, and the units are newtons, meters squares per coulomb squared, times coulomb, and on the bottom there wasn't anything to do, so just 0.250 meters. We can do a little simplifying of the units. So we have coulombs canceling, and we have 1 meter canceling with the meter from the top. And when we do the division, 20.294 Newton meters divided by 0.250, we get 81.1767 Newton meters. And a Newton meter is also known as a joule. So this is the total energy of the system because spheres A and B are 25 centimeters apart. At position 2, our sphere B has moved to a position of 98.5 centimeters away. So we're going to figure out how much energy there is at that point. So total energy of the system, E prime T, is equal to E prime E. So this is the electric potential energy at that point. Because sphere B has started to move, there actually will be some kinetic energy. So the equation will be K Q1 Q2 over the new R distance, and kinetic energy is just 1/2 mv squared. Let's plug in our variables. Coulomb's constant, QA, QB, new distance of separation. This is the kinetic energy, 1/2 mv squared. The mass of the sphere B was 100 grams or 0.1 kilograms. So when we do the math for the first term, we get 20.603, and the units are going to be joules. We're just going to leave the 1/2 mv squared as it stands. We know that total mechanical energy has to be conserved, so the energy I started with equals the energy that I finished with. So 81.1767 joules is equal to 20.603 joules plus the 1/2 mv squared. I'm going to subtract the 20.603 joules from both sides. That gives us, on the left-hand side, 60.5734 joules. Here's our 1/2 mv squared. I want to isolate for v prime. So I am going to multiply both sides by 2 and divide both sides by 0.100 kilograms. So the kilograms cancel off. The 2's cancel off on the right hand side, so we're just going to be left with v prime squared. So on the left hand side, when we do the math, we get 1211.469, and the units are joules per kilogram, is equal to v prime squared. So the base unit of a joule is actually a kilogram meter squared per second squared. So now we've got kilograms on the top, kilograms on the bottom. So v prime squared is equal to 1211.469 meters squared per second squared. Take the square root of both sides. You get a v prime of 34.806 meters per second. Rounding it to 3 sig digs, 34.8 meters per second. So that will be the speed of sphere B when it's moved to a position of 98.5 centimeters.